Okay, we're going to move on to our last part of trig derivatives. So in the last lesson we took care of figuring out how the trig derivative works. So we had derivative of sine was cosine, derivative of cosine was negative sine, and all the rest. And we looked at product rule, chain rule, quotient rule, all the things we learned before. So now today we're going to wrap up trig derivatives by doing higher order and implicit. So just like before with regular derivatives, we could find our first derivative, second derivative, third derivative, and so on. The same thing applies for trig. We just got to be careful. Sometimes they get a little bit complicated. You start getting into product rule, quotient rule, and all those kind of things, which happened before as well, but just follow the same procedures. So let's do the first three derivatives. So in this case, if our equation is sine 2x, derivative of sine is cosine, and we'd have to multiply the derivative of the brackets, which is 2. So there we go. Our first derivative is 2 cos 2x. That one was pretty simple. So now let's do our second derivative. So second derivative, we basically just do the same thing again. Our 2 would stay the same. Derivative of cosine becomes negative sine 2x times 2 again. So for that one, let's bring the 2 and the negative out front. So that would give us negative 4 sine 2x. So that one's good. So our third derivative now should be almost the same again. So derivative, or let's leave the negative 4 alone. Derivative of sine becomes cosine, and 2x derivative would be 2 again. So bring that to the front, and we would get negative 8 cosine of 2x. So you can see it works pretty simple with sines and cosines. They just sort of flip back and forth, and it goes positive, positive, negative, negative, and so on. So that would be the first three, and we could keep going. The next one would be 16 sine 2x. Then it would flip back to 32 cos 2x, and then back to negative, and so on. It would keep following that pattern. Let's see what happens with tangents, though. This one could be a little bit more difficult. So if our original equation is tan, we know from our formula sheet the derivative is secant squared. But let's write that as secant x in brackets squared like this. So now we can see that our derivative, our second derivative, we would use chain rule. So let's bring the 2 down in front. So you'd have 2 secant x to the power of 1, but now the derivative of the inside is secant times tan. Okay, so if we simplify that, let's rewrite this as 2 secant squared times 10. And there's no other simplifying that we can do, so now you can see the third derivative becomes a bit more of a problem because we're going to have to do it as a product chain combo. So let's see what happens. If I make our first f value 2 secant x squared, just like we just had, so that derivative would be 2 times 2 would be 4, secant to the 1 times secant and tan again. Okay, we can combine that in a minute, and then our g would be tan x. So that derivative ends up being secant squared. So now let's follow our product rule and see what happens. So I'll do it up here where I got a bit more room. So we'd have those two being multiplied. So that'll give us 4 secant times secant. So let's write that as secant squared times tan. So that would be tan squared. And then the other two would be plus, we have 2 secant squared times secant squared again. So that would actually give us 2 secant to the 4th. So that would be our third derivative. And you can see we can probably do a little bit of simplifying. Let's pull out a common factor of 2 secant squared. So then the leftover would be 2 tan squared plus secant squared. And that's probably as far as we can go. Tan squared plus secant squared isn't an identity. It's not one of our nice identities, and there's a 2 on there, so that doesn't help too much. So I think that's it. I think that's as far as we can go with that one. So do the product rule, follow your steps, common factor out as much as you can, and that's it. So you can see second, third derivatives work the same as before. Just be careful of product rule, chain rule, all the same things that we had to be careful of with regular derivatives. So also with trig, we can do implicit, same sort of idea. So we just go left side, right side, do your derivatives just as they are. Remember, when you do the derivative of y, you have to multiply by dy dx. So you can see this one that I copied out of the textbook. Derivative of sine y is cosine y, but because we have a y, we need to times it by that dy dx term. The other side is pretty good. Cosine turns to negative sine. The derivative of 2x is 2, so that's why we had to times by 2. It'd probably make more sense to put that 2 in front. So let's rewrite our final answer as, like if we move this 2 to the front, so we just basically get negative 2 sine 2x divided by cos y. And just like we did with implicit before, if we were actually going to calculate slopes or whatever, we would need the x and the y coordinate. So typically with these kind of questions, I would say calculate the slope at, let's suppose it was an angle of pi by 4 or something like that. So it doesn't matter too much because usually you can get that coordinate, right? So at pi by 4 we would know our sine value and cosine value would both be root 2 over 2. So in this case, it should work fairly easy if you had to find that slope value. But let's just worry about doing the implicit today. We can worry about the equations and that kind of stuff a little bit later on. So here's a different one. Let's kind of follow their steps to see if we can understand what's going on. So the first part is we have x times cos y. So you can see they're doing it as a product rule. So derivative of x is 1, derivative of cos y would be negative sine. And you can see that because it's a y, they needed to multiply by dy dx. So we'd have negative sine y, dy dx. So you can see that's what's below. X times the negative sine dy dx plus derivative of that would be 1 times cos. So that left side looks good. The right side is just a regular derivative, so derivative of sine becomes cosine, keep the brackets the same, and then the derivative of the brackets, derivative of x is 1, derivative of y becomes dy dx. So when we had two dy dx's before, remember we had to try to get them all on the same side and factor things out and so on. So this one's a little bit more confusing because we have the cos x plus y times 1. So before we do this second step, you can see this first part is good. They just brought the negative out front to get the term below it. Then cos y is fine. What they did on this second one is they FOILed this out. So they went cos x plus y times 1, which is the same thing, and then cos x plus y times dy dx. So they FOILed that out and then moved it to the other side. So they kind of skipped a step, but you should be able to see that it works the same as we normally would. Okay, so that's what that one would be when you FOIL it out. So you can see the first term, the dy dx, is the same. They brought this cos x plus y dy dx to the other side. That's why it's negative. The plus cos y became negative on the other side, and the regular cos xy stayed the same. Then they factored out a dy dx, so they didn't write that step either. So let's do that below here. So factor out a dy dx, and we would get minus x sine y. Oops, I didn't write that quite right. Let's fix that. So factor out a dy dx, we get minus x sine y. And the other term is that minus cos x plus y. And then all the stuff on the other side would stay the same. And then you can see the last step is divide by that bracket that we factored out. So this final answer looks good. So with this one, there's not much to simplify. Just leave it there. Because again, remember, if we're actually going to calculate the slope, you would have the x and the y coordinate. And from there, you'd be able to calculate the slope quite easily. So let's try a couple more. Make sure you get the hang of these. So again, let's follow our steps. So we want to keep your implicit. Don't start rearranging order unless it would make it easier. But in this case, it's good the way it is. So let's just do the derivatives the way they are. So derivative of sine y would be cos y times dy dx. Derivative of y by itself is 1, but because it's y, we need dy dx. And then on the other side, derivative of cos is negative sine x. Derivative of x is 1. So just like we did on the last one, we need to factor out that dy dx. So we'd get cos y plus 1. Don't forget the 1, because that derivative of y, there was a 1 in front there. We need to hold that spot. And then the other side would be negative sine x plus 1. Divide your brackets out, and we're done. So negative sine x plus 1 on the on the right side, divided by our brackets on the left, cos y plus 1. So first derivative, pretty straightforward. If we're going to do the second derivative now, we'd have a quotient rule situation. And remember, those where it gets a little bit kind of tricky. So we don't often do second derivatives with trig, but maybe we'll look at one over the next couple examples if there's one that works. So here's a double chain. So do the same thing like we did before. So treat the chain on the inside. Think of that as being just sort of your second set of brackets. So derivative of sine is cosine. Leave the brackets the same. Now derivative of cos x would be negative sine x. And that's it for the left side. Do the right side the same. So derivative of cos becomes negative sine of sine y. Derivative of sine y is cos y dy dx. And in this case, there's not much we can do other than just divide the two sides out. So I'll just leave all of that on the one side. Let's just bring this over. So we'd have cos of cos x as one term times negative sine x as the second one on the top. And the bottom would be the negative sine y, negative sine of sine y times cos y. And you can see there's really nothing that can cancel. Everything's different other than we could get rid of the negative ones. That's probably it. Nothing else that would work that well. So I would just stop there and just leave our dy dx as that as our final answer. Okay, here's another one. This one you got to be careful. We can see we've got the left side looks good, but we got to remember to treat this as a product rule on the right side. So maybe let's deal with that first. So if f is 2x, derivative would be 2. If g is y, derivative is dy dx. So just on the right side, let's just deal with that since we're working on it. Do our product rule, so that would give us 2y plus 2x dy dx. The left side, do our regular derivatives. So derivative of sine is cosine. Derivative of cos 2x would be negative sine 2x times 2. Let's put the 2 in front. And you can see we're pretty much done. So just divide or subtract the 2y out. Let's rewrite this as cos x minus 2 sine 2x minus 2y equals 2x dy dx. So our last step would be divide everything by that 2x, and we're done. So cos x minus 2 sine 2x minus 2y all over 2x. And again, this would be a pretty nasty one to do second derivatives on, so we'll stop there. Let's do another one. Here's kind of a double product rule situation. So let's try, let's do our product rule first. So this one would be our f and g term. The second one would be similar. So let's write out our terms. So if f is sine x, the derivative of that becomes cos. If g is cos y, derivative of that is negative negative sine. Dy dx. And then for our other side, do the same thing. So if f is cos, derivative is negative sine, and if g is sine y, derivative becomes cos y dy dx. So we should be good. We should be able to write all these out. So let's do our first two. So we get cos x, cos y. Do our other two. So it becomes minus sine x, sine y, dy dx. Do the same thing for our other two. So now we have minus sine x, sine y. And then our last two would be plus cos x, cos y, dy dx. And on our original equation we had equal to 1, but that derivative would be 0. So it looks quite confusing, but you can see we have lots of similar terms. So let's see what happens. Let's factor out our dy dx on the one side. So that would give us cos x, cos y, minus sine x, sine y. And let's bring all of our other terms to the other side. So we have the sine x, sine y. Let's write them kind of in opposite order. Let's go minus cos x, cos y, plus sine x, sine y. And this one now, when we divide it out, we should get a pretty nice simplification going on. So we can see that both brackets are almost the same. So what I'm going to do is I'm going to write the right hand side. Let's take a negative factor out. So that would make it cos x, cos y, minus sine x, sine y, which you can see is the exact same thing as what we're going to divide by. So the nice part is all of this stuff should cancel except for the negative 1. Oops. So in this case, you can see everything on the top is the same as what's on the bottom, other than that negative factor. Cancel those out. Our final answer is negative 1. So that works really nice. So now this one would be a really good one to do. If I asked you to do the second derivative, our final answer would be 0. So that one works really, really well. Let's try to backtrack. Maybe let's try one quick second derivative before we quit. So let's try, I won't go back because I can't find it, but let's try maybe one more quick one, but let's try to do a second derivative, or even third derivative. So let's see if I can open up a blank page here. Okay, so this looks like it works. I got a blank page. Let's start with an easy one. Let's do something like sine y plus cos x equals 1. Something like that. So let's do implicit. So we'd be able to do cos y dy dx and negative sine x equals 0. So this would be a pretty easy first derivative. We end up getting negative sine x. When we bring it to the other side, it would be plus sine x divided by cos y, and we're done. So that's our first derivative. So now second derivative, if it was sine x over cos y, we could make it tan x, and that would make it really easy. But in this case, we have to do implicit. So we're going to have to do it as a quotient rule. So let's make our top sine x, so that derivative would become cos x, and the bottom is cos y, so that derivative is negative sine y dy dx. So if we follow our quotient rule steps, would be those two. So we have cos x, cos y, minus, and then we have already a minus there, so that'd be plus sine x, sine y, dy dx, all over the bottom squared. So the bottom was cos y squared. And we're good, except now we just need to remember with second derivatives, we had to plug in the first derivative answer. So let's take this sine x and resubstitute it over here. So that should give us minus cos x cos y. And we'd have sine times sine would give us sine squared x. And we have sine y divided by cos y, so let's even write that as tan y. And then our bottom would still be cos squared. And that would be good enough. So if you didn't quite follow what I did there, I just put sine divided by cosine in for our dy dx. The sine and the sine together gave me sine squared, and then sine y divided by cos y, I changed it to tan y, just to not have fractions together. And that's pretty much it. There's no simplifying that we could do with this one. I would just stop there. We could maybe, now that I look at it, we could maybe simplify something to do with the cos y's, right? We have a cos y and a cos y squared. We could maybe do the tan and the cos together a little bit, but it's probably not going to do much, so let's just leave it there, and that's it. Third derivative would be quite complicated. So with trig, often first derivatives are all that we do. Basic ones like this one, maybe the second derivative, and that's it. So we should be good. Our next thing we'll do before we move on to logs and exponents is we'll do a quiz on this trig limits and derivatives before we move on to logs and exponents.